Okay, looks like we're ready to go here. So again, my name is Pat Cunningham. Welcome to a webinar by CA Associates concerning using the ANSYS Workbench environment with SolidWorks CAD geometry. Many of you probably saw this synopsis on our website. The types of things that we'll be displaying today. We'll be showing the bidirectional associativity of CAD parameters between, in this case, SolidWorks CAD geometry and our ANSYS Workbench analysis files. Now, this is not limited to SolidWorks. This is also something that can be done with Autodesk Inventor, Pro E, Unigraphics NX, Mechanical Desktop, and Solid Edge, in addition to a few others. So if SolidWorks is not your preferred CAD geometry and you're using something else that you either didn't hear me speak of or don't see on the list, you can certainly give us a call. We can clarify what the capabilities are between ANSYS and your particular CAD tool. We're going to be doing a very brief demonstration of the geometry modification tools in Design Modeler. Design Modeler is essentially the geometry tool inside of the Workbench environment, and we'll show you how that works today. One of the nice things about performing your modifications on your geometry in the Design Modeler tool versus doing it in the CAD tool is that there's no reason to keep a copy of your CAD part. You can take essentially your fully featured, fully prepared CAD geometry, bring that geometry into Design Modeler, and make the modifications that are necessary to achieve the type of mesh that you need for your particular analysis. And your mesh requirements will be governed by, in many ways, the resolution on the results that you're after, the type of loading that you may be applying, and other things like the type of geometry that you need to model. One of the things that we'll be doing today is making an assumption of symmetry, where we will cut the part, and our loads, our materials, and our geometry will all be reflectively symmetric about that cut boundary, which means we only need to analyze a smaller portion of the geometry. Design Modeler is very, very good for setting up those types of analysis features. We will then bring that geometry into the analysis tool, what we call the ANSYS mechanical tool at version 12, which is the release that we'll be displaying today. And we'll talk about some of the things that happen for you automatically on the simulation side, things like automatic contact generation, some of the automatic meshing capabilities, and then we'll even delve a little bit into some of the manual mesh capabilities that you can add. We'll then talk a little bit about what we can do with some of these things, like the contact regions that are created. How can we use those, not just to connect our parts together, but to do things like interference fits, because we're going to bring in an assembly of parts today. I'll show you how to do some bolt pretension loading. We'll generate a solution, and then we'll talk about how do we use this bidirectional associativity, this connection between our CAD and our analysis tool. So we'll talk a little bit about how to quickly turn around design studies, where we've set up the model once, and then we can parametrically change the geometry and generate new results with a minimal amount of effort on your part, because you've already set up and run that model one time. So I'm going to start by going into SolidWorks, and I'll need to share my desktop here. So just give me a moment. I'm going to bring SolidWorks to the forefront. Hopefully everyone will be able to see the SolidWorks interface. What we have displayed is a pillow block with a shaft going through, sitting on a base. As I mentioned before, we can always do our defeaturing operations inside the CAD tool. Defeaturing would be things like removing details in the geometry that don't play a significant role in the analysis portion. Those would be things like chamfers or fillets in areas where we're not concerned about stress. We can do that in SolidWorks, but again, it requires that we modify our parent CAD file. What we'd like to do ideally is have a tool that allows us to create these geometry modifications without affecting that CAD tool, because that CAD model itself, or that CAD file, has a very specific purpose and a very specific role in our design process. And rather than modify it for other purposes, we have a separate tool that will do that actually better in most cases than in the CAD tool. So to run ANSYS from our CAD environment, you'll notice up across the top we have some pull-down menus. I've got a couple different versions of ANSYS installed. We're going to go with the current release, version 12.1. And to open up ANSYS or launch it from the SolidWorks environment, I simply use the pull-down menu to open up Workbench. Very shortly, you should see the ANSYS 12.1 splash come up. And we'll give it a moment here for the ANSYS project page to open. Okay, so essentially we have opened up a blank project page in the Workbench environment. But you'll notice in a moment that because we launched this from SolidWorks, the SolidWorks part that we had active is automatically connected to the analysis environment. So if I click on that geometry and I look over in the right-hand panel where I have the properties of that geometry, you'll see the parent SolidWorks assembly file listed as the source file for this geometry. We're going to include things today like solid bodies. There are no surface bodies in the part, but we could click that on or off as we choose. And more importantly, we're going to include parameters. So we're going to bring over some very specific parameters that I defined with a common prefix on the SolidWorks side. So I had gone into my features in SolidWorks, picked the key parameters of the geometry, and gave the parameter name a common prefix that I could filter out during the connection process to the ANSYS tool. Let's take a look at what that geometry looks like. To edit it in Design Modeler, we simply right-click and select Edit. And that will open up the Design Modeler tool, and we'll be ready to import the geometry from SolidWorks. Okay, so you should see the ANSYS Design Modeler interface coming up now. The first thing that it's going to ask me is what unit system would I like to work in. What I want to be sure that I do here is use the same unit system that was used to model the part on the SolidWorks side. I've already checked that on the SolidWorks side. I know it's in inches, so all I need to do here is say OK. And you'll notice that I have an attach feature inserted into my tree outline. That's the only thing that we have going at the moment in this new version of Design Modeler. And below, if I click on that attach feature, you'll see the properties or the details of that attach. And they're very similar to what we were just looking at on the project page. We have the source file. We have the base plane for that file. My operation in this case, I'm going to add frozen because I'm bringing in an assembly, and I want to make sure that my parts don't get merged all together in one part. So I'm going to bring them in as separate or independent bodies by indicating that I'm adding them as frozen. Bringing across parameters. Other things that we can bring across that I didn't talk about on that project page, if we've assigned material properties on the CAD side already, we can import those as well, so there's no need to redefine them. Coordinate systems that we may have on the CAD side, those can come across. Other attributes, that would be things like thicknesses assigned to sheet bodies. So we'll go ahead now and we will generate. And you'll notice down, generation says basically go out to SolidWorks, get the geometry, read that parent file, and bring it into Design Modeler. So you'll see we have a little status bar down at the bottom, and here's our assembly file. I'm going to go ahead and turn off my frozen body transparency so we can see the parts a little bit better. And essentially we have 9 independent bodies that came in, the same number that we had on the CAD side. So some of these bodies here, we don't need to include our analysis. Those would be things like we could take the shaft out because we're going to apply a load that represents the shaft. So I'll simply suppress that body here in Design Modeler. We're going to go and take the trainer or the base out, so we'll suppress that. And that's pretty much all. We're going to keep the rest of them here. We have a bearing that's currently combined with the block body. We've got a couple of washers here and some studs. Now, as I mentioned before, we're going to do a symmetry analysis on this. Okay, we're going to assume that we can take up 1/4 of this geometry and apply 1/4 of the loads and analyze just that portion and get the same response as modeling the entire structure for less computational time invested. So I can do that very, very simply in Design Modeler. I go to the Tools menu, indicate that I want to make a symmetry cut. I can specify the number of symmetry planes, 1, 2, or 3. In this case, we're going to do a quarter symmetry solution here, so I'm going to go with 2 planes. And I'm just going to identify the planes that I'm going to use. So I have one plane situated in the center here. It will keep the half of the geometry in the direction of that normal vector, that blue vector on the plane. And then we'll add in a second plane, the global YZ plane, and that will take this forward portion and keep that while we're moving the rest. When we generate that, we'll see that we now have 1/4 of the part. So any additional defeaturing operations that we do from here on only have to be done on 1/4 of the part. So let's take a look. There's a few other things we can do here. I'm not really worried about having the 2 washers in this case as separate bodies. So I'm just going to combine them in Design Modeler into one single body. I need to have that spacing there in order to have the bolt head in the right location. But I can combine the 2 washers into one for my purposes here. So I'm going to use a Boolean operation, and I'm going to unite these 2 bodies. And you'll see that they've been added. I now have one flat washer that's a single body. And that's just going to simplify my meshing operation when I go into the simulation tool. One other thing I've got going here is the bearing and the block are one single body. See, when I pick here, I get both the bearing and the block geometry. This was modeled that way in SolidWorks. This is actually a sample SolidWorks part that comes from their basic installation. So whoever created this part, for some reason, combined the bearing and the block together. In our case, we'd like to have them as separate bodies because we're going to talk about ways to do things like interference fits between a bearing and a block in this case. So I need to separate those into separate bodies. Where I just previously united two bodies in the washer case, now I'm going to separate or divide this section of the geometry into a separate bearing and a separate bearing block. And I do that by using the slice command. So I'll create a slice. I have a couple of options for slicing this geometry. I can slice it by plane, slice off faces. In my case, I have a nice little cylindrical surface that I can use. So I'm going to say slice by a surface and pick on that cylindrical surface. When I hit the Generate button, I've then created a separate body that represents the bearing. Now I'm going to rename that. That's the bearing body, so we're going to rename this guy to the block, so it's easy to identify when we get into our analysis tool. Now there's a whole host of other things we can do with Design Modeler to prep our geometry in terms of meshing operations, in terms of boundary conditions. We're not going to talk about too much more of that today. I'd like to get into the actual analysis tool and start generating some results. But if you have any other questions about Design Modeler and its capabilities, by all means give us a call. And we can elaborate because there's a whole host of different capabilities that Design Modeler has that are very, very helpful and useful in terms of setting up your finite element model. So how do we get this into the analysis environment? Well, we simply return to our project page. Our geometry is ready to go. And I look over on the left-hand side, and I see my analysis systems. And what I'd like to do is perform a structural static analysis on this part. So I'm going to grab that item, that system, and I'm going to bring it onto my project page. Now I'm holding the left mouse button. And there's a couple of different places I can drop it to create standalone systems. But I'd like to connect it directly to this geometry. So the easiest thing for me to do in this case is just to drop it right on the geometry row of my item. And you'll notice that it's indicating that it's going to share that geometry. It creates for me an analysis system with a series of items. And you can see that there's a sharing link or an association between my Design Modeler geometry and my analysis tool. Well, why would I want to have this capability? Why is this necessary? Well, essentially, I could create multiple geometry items. I could bring over as many of these as I choose, have different geometry files, and I can link them to different analyses by simply dragging them and dropping them. So there's a tremendous amount of flexibility between the different geometries that you have. You may want to modify the geometry and keep it, have different variations, different iterations during your design, and still use a common analysis environment. Take advantage of the fact that you've defined mesh controls and you've defined boundary conditions to be able to make yourself as efficient as possible. Now, with my geometry linked, the first thing that I'm going to do is go in and specify my material properties. And I do that by double-clicking on my engineering data row. I will open up the engineering data manager inside the Workbench environment. And my engineering data group, which is basically my materials for this current project, only contains, at the moment, structural steel. And I'd like to add some materials to that. I have a whole host of different materials that I can choose from, different libraries. I can create my own material, add in specific properties. In this case, we're going to keep it fairly simple. We're going to go to the General Materials Library. And when I click on the General Materials Library, the contents of that library are then displayed in the window below it. So I'm going to add aluminum alloy to my engineering data, and I'm going to scroll down a little bit and add stainless steel. So I'm going to have three materials in this particular project: aluminum, stainless steel, and steel, accessible to me on the analysis side. With that complete, I return to the project, and now I'm ready to open up my analysis model and begin to set it up. So we simply right-click and indicate that we'd like to edit. Now in a moment, you'll see the mechanical tool open up. The mechanical tool will automatically transfer the geometry from Design Modeler based on that connection into the analysis environment. We mentioned a moment ago, we can now assign material properties to the different bodies. So in this case, we're going to take our block and we're going to assign to it the aluminum property. So I select the block from the geometry list, and if I look down in the lower left-hand corner, my material assignment is there, and I can pick from any of the materials that I've added to this particular project. We'll specify the block as aluminum. We'll specify, I can do this as a bulk selection. I can pick the socket head and the flat washer, and we'll define them en masse as stainless steel. And then we'll go back to the bearing. We'll leave that as structural steel. Now, to very easily confirm that I've assigned these properties correctly, I can go to the main geometry item and indicate that I would like to display my parts in terms of their material designation. So I select material. I get a nice little contour of aluminum in gray, stainless steel in blue, structural steel in green, and I can visually confirm that I've assigned the correct materials to my parts. Okay. Well, let's talk about these geometry parameters for a moment. I'm just going to drop back to Design Mahler and take a look at the details of my attach function. When I attached that geometry, I had a series of parameters come along with that attachment. And you can see they all begin with that parameter prefix DS, which is the prefix that I manually assigned to them when I brought them into the Workbench environment. So in order to take advantage of these now in Workbench, I can pick and choose from the parameters that I brought in. We're going to pick a couple to carry along with us through the process here. So we're going to start with, let's take a look at the bolt spacing. We'll add that as a parameter. And then we'd also like to have the bearing center brought in. So I'm going to carry two of these input parameters. One of those parameters, if I go back to SolidWorks, I can see that one of those parameters defines the spacing of that bolt geometry. The other defines the height of this bearing. So for instance, now that I have included those parameters, you'll notice when I return to my project page, I automatically have this parameter set defined, which is sharing parameters between the geometry now and the analysis tool. If we double-click on the parameter set, we'll see our list of input parameters that we just defined. We're going to work with these a little bit in addition to adding output parameters after we've generated a solution to talk about doing sensitivity studies with our parameters. But just to illustrate how this whole thing works, we're starting out with this bearing center dimension of 3 inches. We're going to go and change that right now in the parameter manager to 2.25. When I return to the project, I can indicate that I'd like to update the project, or in other words, send that parameter information back to SolidWorks. SolidWorks will regenerate that geometry for that base parameter value now of 2.25, feed it to Design Mahler, which you'll see in a moment is updating as we speak, and then send that same information over to the mechanical tool. So in one menu pick, Update Project, I updated the entire process that we have gone through thus far. And you can see that the geometry has visually changed with respect to that bearing height dimension. Where before we had a much thinner region of material above the bearing, now we've kind of centered that or dropped it down closer to the center of the block. Okay, we'll be doing that again. So that's something we like to illustrate as much as possible because it really shows the ease of use of and the flexibility of having a fully parametric model with your analysis tool. So let's go back to our analysis environment where we are right now, the mechanical tool, and let's take a look at some of the other features that we have. In addition to our geometry, which we had talked about already, assigning our material properties, we have a group of coordinate systems. We have our global Cartesian coordinate system. You can see it's shown below the part. And then we have the global XY and the global YZ planes, which were used to cut those symmetry areas in Design Mahler. I believe someone's put us on hold, and although I do appreciate the jazzy music, if you could mute your phone, that would be very helpful. Okay, well, I guess I'll just I'll groove along with the music here. So moving along, what I'd like to do is put an interference fit on the bearing block. And by putting in that interference fit, I'm going to introduce a hoop stress in the part. So in order to evaluate a hoop stress, I'm going to need to have a cylindrical coordinate system. Christina, if you could try to mute, thank you very much. Okay, now we're back to the demo. So in order to put in a coordinate system, again, there's a couple of different ways that we can do this. We can bring coordinate systems over that are defined on the CAD side. We can define them in Design Mahler, or we can define them locally here in the simulation tool. I'm going to pick on this surface here, and indicate that I want to add a coordinate system, and you'll see that the coordinate system is snapping to the centroid of that cylinder. Now, I'd like this to be a cylindrical coordinate system with the axis along the length of the cylinder. So I'm going to come down here and specify my primary axis as the z-axis direction, and my type of my coordinate system or plane to be cylindrical. And you can see the little symbol updates indicating that I have an axial z direction, a radial x direction, and a circumferential y direction. So any items that I define or visualize with respect to that coordinate system will be in terms of radial, tangential, and axial directions. To make that easy to identify, I'm just going to rename it. I'm going to call it the bearing cylindrical, so that I can very easily pull that off for future use. Okay, let's move down to the symmetry section now. If I open that up, you'll see I have two symmetry regions are defined. Now, these were created automatically by virtue of the fact that we used the symmetry tool in Design Modeler. So there's a lot of talking going on between Design Modeler and the mechanical tool. When you define symmetry regions in Design Modeler, they automatically become symmetry boundary conditions in Design Modeler. So that's, in mechanical. So there's no need for me to put any additional boundary conditions on these cut planes. They're automatically defined by virtue of that symmetry tool. We could choose to delete them if we didn't want to use them, but in our case, we're going to utilize them because it's very convenient, and I don't have to repick all of these surfaces. Moving on beyond symmetry, we have the connections region. Now, to make the connections easy to identify, we're going to right-click and rename them based on definition or their part names. And you'll see that we have three bonded contact regions. Now, these were created automatically when we brought the geometry into the mechanical tool. If you look down in the details of our connections region, down where my mouse is here in the lower left, you'll see that we're specifying that we want to generate contact automatically whenever we update the geometry. That's set to yes. There's a tolerance value, which is used to determine whether or not two surfaces are close enough to warrant a contact region. That can be defined manually. That can be made more tight or more loose depending on your particular situation. And if you ever find that you can't get your contact regions defined automatically for a particular reason, you can always go and insert a manual contact region where you just specify manually the target and the contact faces. So looking down here, I'm going to take a look at my contact regions. I have one bonded contact region with the contact body surface shown in red. That would be the top of the block, and the target surface body shown in blue, which is the underside of the washer. Bonded means that these two surfaces cannot move with respect to each other. They're essentially glued together. In our case, we're going to assume that we have sufficient friction at that interface and sufficient bolt pretension that there shouldn't be any movement. So bonded is going to be our initial or simplifying assumption for that connection. If we take a look at the second region, we have a bonded. Again, all these are defined by default as bonded, but we can always change that performance. In this case, we have the contact region between the bearing and the block itself, and we would like to be able to put in an interference fit between those two bodies. So we're going to change the contact type from bonded to one of the other capabilities, one of the nonlinear definitions of this contact. You can see we have a couple of choices here down on the lower left between bonded contact, which, as I mentioned a moment ago, means glued together. No separation is also a linear representation of this contact. It means that we can allow for small degrees of sliding between the surfaces, but they cannot separate. Then we have our nonlinear contacts, the frictionless, where they can freely separate or slide. Rough means essentially infinite friction, so there's no sliding allowed, but that the surfaces can freely separate if there's sufficient force to do so. And with frictional, we'll be prompted to supply a coefficient of friction. We're going to keep it fairly simple in this case, go with a frictionless connection between the bearing and the block. And now we have the option to input an offset. Well, you'll notice that it's asking me for an offset in meters. My default unit system is meters, but at any point in the process during my mechanical setup, I can go up to my unit systems and change it to something different. I like to work in inches, so I'm going to set my displayed units to U.S. customary inches. And now I see that inches is represented as the offset dimension. Well, if I want to put an interference on this part, one of the things that I need to know first is what the geometric situation is. I don't know how this was modeled. I did not create the CAD model myself, so it could have an initial interference. It could have an initial gap, depending on the way this part was modeled with respect to its nominal dimensions and its tolerances. So I need to determine initially what's going on between those two surfaces, and I can do that using my connections region. Right-click on connections and insert what's called the contact tool. The contact tool has in it an initial information section. So if I right-click here and generate initial contact results, what ANSYS is doing is going out and creating a mesh on my part and then evaluating the initial condition of that contact. What is the proximity of the contact elements to the target elements in this system? Now, if we take a look at our results, in fact, we can simplify this a little bit further by taking out some of the linear ones. We don't really care about those. So I'm going to go to my linear contacts and remove them, and then just regenerate my initial contact results. So we're looking at the initial information for the nonlinear contact only. So you can see we have an initial geometric penetration between the parts of about 1.4 times 10 to the minus 3 inches. Well, I'm going to want to put a little bit more interference in on that, so I'm going to add an interference value to that. So I go to my frictionless support, I come down to my initial offset, and what I'm going to do is add in 1/1000th of an inch radially, or 2/1000 on the diameter, to that initial value. I can go back, recheck that initial contact information again, and I should see that under the initial information, my initial penetration is going to be the sum of those two values. So that's all it takes for me to put in this interference fit between the two parts. I'm actually utilizing the contact region to push it towards the target and create that interference fit for me. So we'll get back to that as we start to apply the different loads and set that up in our process. Before we do that, though, we'd like to take a look at the mesh that was created. Now, the Workbench environment will always create for you a default mesh. It has some basic settings that give you a good starting point. Very often, what you'd like to do is start out with that initial mesh, put some boundary conditions and some loads on your part, and get an initial solution, taking a look at only the deformation results. Make sure that your deformation results and that your reaction forces are matching your applied load, and once you're satisfied with that, go back and start to apply more local or specified mesh controls in regions where you expect to get sensitivity to stress. So in my case, I know I'm going to be looking at the hoop stress in and around the bearing, so I'd like to get a little bit more resolution in the block. You'll also notice here that the bearing, although it was not a general shaped item, was automatically hex mesh. So there is some intelligence built into this ANSYS mesher that will mesh bodies like the bearing and also the washer with a fully brick mesh if it can. Which one should I use, bricks or TETs? It really doesn't matter. What it comes down to is that geometrically, typically fewer bricks are required than one tetrahedral mesh to fill the same volume. So ANSYS will try to, whenever it can, put in a brick mesh simply to reduce the element count for the same amount of fidelity in the result. So let's go in now and let's refine the mesh locally around the bearing region on the block. I've got a couple ways I could do this. I could go into the sizing controls globally and specify a sizing for the entire part. I could specify a sizing on just the bearing body. But there's actually a slicker way for me to do this. I'm going to go in and put in a localizer specified mesh control on the bearing block itself, only in the region where I'm interested. So I'm going to insert what's called a sizing. And I want this sizing to apply to the bearing to the entire bearing block. However, I only want my mesh control to be refined around the bearing itself. So I'm going to use a special type of sizing in this case, referred to as a sphere of influence. I can center that sphere of influence at my bearing cylindrical coordinate system and specify a radius of overlap. So when I put in a value of 1.5, see where the red sphere appears, where the overlap between the sphere and the specified bearing body occurs, I'm going to get the mesh refinement that I'm asking for. Everywhere else outside the sphere is going to go back to the default mesh. So I'm focusing the mesh in the discrete region where I'm interested in the result. So we're going to go now and add an element size. We'll give it 1/8 of an inch at that location. And let's take a quick look at the mesh for a moment here, because when we update it, we're going to see that the mesh in this region has been refined with respect to that control. So I'll right-click, generate the mesh. And now you can see that we have those elements of 1/8 of an inch in size in and around the bearing, with the remainder of the tetrahedral mesh in the bearing block going back to its default size. So very quick and easy way to put that mesh control on. Doesn't require that you have divisions in your geometry. Allows you to really localize or focus the mesh fidelity in your area of interest. Okay, so what do we have? We have bodies with materials defined. We have symmetry controls or symmetry boundaries defined automatically. We have contact regions that have been automatically defined on our part, and we have a mesh. So now we're ready to go ahead, put some loads and some additional supports on this part and generate a solution. So we're going to come down to our structural analysis folder, and as we mentioned before, we have symmetry boundaries on these two faces as shown, but we need to constrain this in the vertical direction. So I'm going to go in now, and I'm going to insert what's called a frictionless support on the bottom of the block. And then I'm going to apply a bolt pretension. I'm going to make the assumption that we're bolting this block down onto some rigid block. So I'm going to apply a fixed constraint to the bottom of my bolt. So that will act against the bolt pretension to pull the bearing down onto this rigid part that we're assuming exists beneath the bearing itself. Okay, so I have my frictionless support in that direction, my fixed support. I've taken care of all the degrees of freedom in my system. And now I can go to start to apply some loads. Well, we're going to do this in a couple of load steps. And the reason that we're doing this is the process by which we would normally assemble a system of this nature would be to first insert the bearing, typically by heating up the bearing block and inserting the bearing and allowing it to cool around the block. That would introduce our interference fit. The second step in the process would be to bolt this thing down to something, right? Bolt it down to whatever mounting fixture it's going to be attached to, and then apply some load to the bearing. So we're going to follow that process by adding in multiple load steps. So I'm going to come to my analysis settings, and I'm going to indicate that I'm doing a three-step process. Now, in my first step, I want to introduce the interference fit, and I've already done that by assigning it in the contact region. So that's all I need to do for this first load. For my second load, I'm now going to introduce a bolt pretension. Okay? So the bearing block has been heated up, the bearing has been inserted, we've allowed it to cool and establish the interference fit. Now we're going to bolt this thing down to the table. So I'm going to apply a bolt pretension to the shank of the bolt. And you'll notice down in my tabular data that I have three steps. And I'm going to define how, or the process or sequence by which this bolt pretension is applied. In that first step, as I mentioned before, all we're doing is applying interference fit. So we're going to leave that bolt pretension section open. In the second step, we're going to load it. We're going to put on, in this case, 100 pounds. Now I'm making a symmetry assumption, so in reality I'm putting 200 pounds on each bolt because I have a half symmetry assumption on the bolt. And then once that bolt pretension is defined, I'm going to lock that down. I don't want that to change as I apply a subsequent load. So we keep it open for the interference fit, we load it, and then we lock it down for the last load step. Okay, so we've heated this thing up, inserted the bearing, bolted it down to the table, and now it's time to apply some load to the bearing itself. So we're going to pick on the bearing surface, right-click, and I'm going to insert a bearing load. Now I have to give the bearing load a direction, and essentially what a bearing load does, in a specified direction, so we're going to go ahead and go by components here, and indicate that at load step 3, in the Y direction, which is this vertical direction, I'd like to put a load of 100 pounds on that bearing. And again, in reality, I have a quarter symmetry section of that cylinder, so I'm actually applying 400 pounds to that bearing. I want to make sure that this is just put on in the last step. So in load steps 1, with the interference fit, there's nothing. Load step 2 with the bolt pretension, there's nothing. And then during load step 3, I'm going to ramp up that load from 0 to 100 pounds. Now, the nice thing about this bearing load is in the direction that I've specified, it figures out essentially what the projected area is over a 90-degree swath of that region. And it puts in a force distribution that acts like a shaft picking up on the bearing face. So it's not going to be applying it to the entire surface. It's only going to be applying it on the projected area in the direction of the applied load. So we've got all of our boundary conditions. Now we can go and insert some results. We'll take a look at a directional deformation. What I'd like to do is look at a hoop stress here. So I'm going to rename it. I'm going to call it radial deformation. And that radial deformation is going to be an x-axis deformation with respect to that cylindrical coordinate system that I used before. So it'll be in the direction of this local x. We can also insert stress value. We're going to take a look at the hoop stress in this case. So we'll take a y direction stress with respect to, again, the bearing cylindrical coordinate system. And we'll rename that to be hoop stress. Okay, I can add in additional results later. Let's generate the solution first, and then we'll go back and talk about what we found. So to generate the solution to this problem, I'm simply going to right-click over here, click on the Solve button. At this point, all of the information that we have defined in this outline tree is being distilled down into an analysis file. It's being sent to the ANSYS solver. If you look down on the bottom of my program screen, you'll see an ANSYS batch item. That means that ANSYS is currently running, and it's evaluating the solution of this problem. We can further see that that's happening by the status bar shown up on the top of the screen. In addition to the solution information, we can look at the ANSYS program output, which is actually the ASCII scrolling of that output, or if we'd like to see this graphically displayed, since we're doing a nonlinear analysis here with that nonlinear contact, we can take a look at the equilibrium iteration results and how they are displayed in terms of our overall result. So you can see we did a couple of equilibrium iterations, we converged on the load step, and we're ready to go here. We have our solution. So let's set our scale to true scale in this case, and we can see that that interference fit is resulting in a negative radial deformation on the bearing, so the bearing is being squished downward, and the block is being pushed outward in that radial direction. If we take a look at the hoop stress, we should see a similar response in the first load step. What we're seeing is a negative value for stress in the blue areas. That would be a compressive hoop stress versus a positive value in the outer regions of the block. So the block is being put into a tensile hoop condition, and the bearing is being pressed down by the interference fit being put into a compressive hoop situation. So we can add in other results and evaluate them at this point. We may want to look at the stress more specifically on the surface of the bearing block. So we'll go in here now, and we'll insert a few more stress results, things like maybe the von Mises stress. We'll take a look at it on all bodies, and we'll also insert the von Mises stress and scope it to just this surface of the bearing block. We can also put in, we can make a copy of this current hoop stress result and look at it on just the bearing block surface itself. Now, anytime we add these results, we need to right-click and evaluate them. It basically instructs ANSYS to go out to the result file, grab the result itself, and bring it back for us to view. So here's our equivalent stress result, or our net stress in the system. Here's the equivalent stress being scoped to just that bearing or the block surface, and there is also the hoop stress on the surface itself. So now we can pick from these various output quantities. So let's go to the radial deformation, and let's keep track of the maximum value of that radial deformation. Let's go to our equivalent stress, and let's take a look at the maximum value of that. So we might want to rename these things so that we can identify them later. Let's just say equivalent stress. Rename. Entire system. And then this one would be equivalent stress bearing block. So you have full control over these items. You can edit the names, again, just so that you can better identify what was done here for later purposes. So we'll keep track of that maximum value there. And again, I create or define these as output parameters simply by picking on the box next to their value in the details menu. So that's our solution to our basic problem. Now let's talk about using this. We've got it set up. We're happy with the result. We're happy with the mesh. What we'd like to do now is take a look at the sensitivity of this design to changes in the parameter values. So we can come back to our project page, double-click on the parameter set item, and we'll see that to our parameter set, we initially had our input parameters, or the geometry parameters that we specified. But in addition to that, we have several output parameters that we just defined in the mechanical tool. Those would be things like the radial deformation, the equivalent stress, and then the equivalent stress on that surface. So we currently have values associated with them, as we can see in that column from that initial solution. But what we'd like to do now is have the ability to do some sensitivity work. Well, going back to my project here, I have an initial design. If I'd like to keep this initial design and still have access to that result, the full result over the entire body, the best thing for me to do is to right-click on the model and duplicate it. When I duplicate the model, I'm going to create a complete copy of it. And that copy will be added to my project. Now notice that the geometry is being shared between the two, but the models are separate. So when I edit this particular model, it's also parametrically controlled. I can choose to update the geometry on this model only, regenerate this result, but still be able to compare it to the original result that I had. So that's one way of doing this, to basically keep separate copies or separate models of each part so that you can go back and fully interrogate the geometry later. Another way of doing this is to use the parameter table to do a quick sensitivity study using one single model. You'll notice that over here on the right-hand side, my table of design points currently contains only the initial design point. But we can, at this point, go in and add in additional design points. So let's see what happens if we raise the bearing location from 2.25 up to 2.5. Right. We're going to keep the second diameter, the bolt dimension, constant. We'll go in now and we'll add a third point with the bearing at 2.75. So what I'm doing here is generating or defining a table of my various design points. And I can choose to either update these individually. I can pick on a particular row and update just that selected design point, or I could update all of the design points in my table. So if I had a duty table, or if I had a particular design study that I wanted to perform based on some tolerance value for an input variable, and that could be geometric, it could be a material input, it could be a load magnitude. Rather than doing this all manually, I can set up a duty table where I fill out the required values for the input, and then in one particular shot, right-click and evaluate the results all at once. Now, when I do that, though, I have to keep in mind that I'm using the same model, so that each time I regenerate a design point, the previous one will be overwritten. And that's why I mentioned making a duplicate of my model versus doing this from a tabular standpoint. So if you want to keep copies of your original model so that you can compare and contrast, the best approach is to make duplications and manually update those duplications, or modify the geometry and then manually refresh each individual item. If you're not worried about keeping the original and you'd just like to be able to track the result that you've specified, you can use one simple model to do that by filling out your table, and then, again, using the one single button to update those design points. So let's just pick one of those design points right now. We'll pick design point 2. And actually, let's go with design point 3 because that's 2.75. And let's say we're going to update that current design point. So what that tells me right now is that it has to shut down the mechanical window because it's going out now in batch mode. And it's instructing SolidWorks to update that design parameter to 2.75. Give us the new geometry, and then it's going to run through the process of regenerating that result and filling the table with the result values for that particular configuration. Move our bar up here so we can keep an eye on the progress. So at this point, it's telling me that it's updating them. Okay, it looks like we had a little blip in the power. Hopefully everyone can still see my display here. So I started to mention a moment ago, we're updating the model cell in the static structural analysis. So it's currently regenerating that model, and now it's rerunning that analysis for that new geometric configuration. So we'll just give that another moment to finish up, and we should see that our design point row is then populated. Okay, while we're waiting for that to finish up, I think at this point it's a good time for us to open up the phones to any questions. So Christina, you can conclude recording the demonstration at this point.